tipping points in the climate system. So in my diagram here, I have tipping points kind of sitting over here by themselves. So tipping points are kind of this transition between, we're changing global temperature and then something happens, and then that can filter down into changes in extremes, which then can filter into changes in social and natural systems, impacts on social, natural systems that we care about. And so the whole class today will be on what tipping points are. So here's my class learning outcomes for today. So we have 4. So I want you to be able to define what a tipping element is. So this is a new vocabulary word, and a climate tipping point. So those are our 2 main vocabulary words. I want you to be able to explain the difference between a tipping point in the climate system and the more popular definitions of tipping points that exist out there. And I'm going to be kind of talking about that in terms of the way that the tipping point is defined in Malcolm Gladwell's famous book called The Tipping Point, because I think that kind of exemplifies what the popular notion of a tipping point is. I want you to be able to explain why it's important for something to have a self-sustaining aspect to it in order for it to be a tipping element in the climate system. And I want you to be able to list 4 potential tipping elements in the climate system. First, why are we talking about potential tipping points in the climate system? So the motivation is that these things called tipping points can be potentially very impactful. They can represent some of the largest impacts of climate change on humans and on ecosystems. And another reason is that this vocabulary word, tipping points, has really penetrated into the forefront of contemporary discussion on climate change. So you'll hear this word a lot in news stories about climate change, and you'll hear a lot of the concepts that we're talking about today kind of wrapped into coverage on climate change. And so just an example of that is some of the language used by Greta Thunberg in her famous, in the climate world anyway, famous speech to the UN in 2019. And this is just an excerpt with some bolded phrases that are things that we're going to look at in more detail today. So the popular idea of cutting our emissions in half in 10 years only gives us a 50% chance of staying below 1.5 degrees. So she's kind of invoking a threshold, potentially a tipping point there. And the risk of setting off irreversible chain reactions. So irreversible is a concept that we'll talk about today. Chain reactions, we talk about a lot in climate science. Chain reactions beyond human control. 50% may be acceptable to you, but those numbers do not include tipping points. So there's explicitly talking about tipping points. Most feedback loops, which is again this kind of chain reactions type thing. Additional warming hidden by toxic air pollution, or the aspects of equity and climate justice. So again, just an example of the language that's out there that is very prominent. And so we want to kind of understand these words from a scientific perspective and establish what our best understanding is of these concepts. So starting from the kind of beginning, backing up where this term tipping point came from in the first place, it's kind of ironically related to coal. So it originated in industry in the 1800s with these coal carts. So these coal carts, you fill them up with coal and you can tip them over to dump the coal out. And so the tipping point is, of course, when you're kind of pushing the coal cart and then it tips over. And so that's kind of that's our starting point, our basis for tipping points. And I think that it's really became popular vernacular after this relatively old book now by Malcolm Gladwell called The Tipping Point, which was released in the year 2000. And Malcolm Gladwell is one of the most successful nonfiction authors of all time. So his books have large penetration into culture. And so a lot of the concepts in this book kind of became intrinsically associated with just the phrase tipping points. And what's interesting is that this book was published in 2000, and a lot of the tipping points that we think about today have to do with the internet and like things going viral or social contagion. And this was like before all of that, really. Internet was nothing like it is today in the year 2000, and so it was before retweets and things going viral on the internet. So in the tipping point, he wasn't talking about hashtags or memes or things like that. He was talking about things like the popularity of various fashions. So one of the chapters in The Tipping Point is about the shoe brand Hush Puppies and how it became very popular kind of suddenly in 1995. And then another chapter is about the sudden decline in New York City crime in the 1990s. So this is the number of murders in New York City in the 40s, 50s, 60s, 70s. So it went up, and then all of a sudden it had a precipitous decline here. And so most of what he's talking about in this book has to do with people and kind of the spread of ideas. And the phrase that gets used a lot for that is social contagion. So I'll just kind of read two passages here that like exemplify the type of thing that he means by tipping point. So the tipping point is the biography of an idea. The idea is very simple. It is that the best way to understand the emergence of fashion trends, the ebb and flow of crime waves, or for that matter, the transformation of unknown books into bestsellers, or the rise of teenage smoking, or the phenomena of word of mouth, or any number of the other mysterious changes that mark everyday life, is to think of them as epidemics, ideas and products and messages and behaviors that spread like viruses do. So this kind of viral video is using that language of that one person passes it to another person, just like a virus, epidemic or a pandemic, right? And then this is another part of his definition. So he has three characteristics of tipping points. One is contagiousness, so thinking about how ideas spread among people. Two is the fact that little causes can have big effects. So that's this kind of like straw breaking the camel's back aspects, that you have something build up, and then you have a relatively small cause a big effect. And then three is that changes happen not gradually, but in one dramatic moment. And so these are the same three principles that define how measles moves through a grade school classroom, or flu attacks, or how flu attacks every winter. Of these three, the third trait, the idea that epidemics can rise or fall in one dramatic moment, is the most important, because it's the principle that makes sense of the first two and that permits the greatest insight into why modern change happens the way that it does. The name given to that one dramatic moment in an epidemic, when everything can change all at once, is the tipping point. This is one of the main differences actually between climate tipping points and the tipping points that Malcolm Gladwell describes here. So for climate tipping points, we are going to be using the climate version of the tipping point book. And that is this paper published in 2009 by Timothy Lenton. And so this is kind of the most famous, highly cited paper on tipping points, and it's called Tipping Elements in the Earth System. And so there are some very important fundamental differences between what I'll call Gladwellian tipping points, so the Malcolm Gladwell tipping points over here, and how they're defined in the climate system. So first of all, this is our first vocabulary word here for my class learning outcomes, is tipping element. The tipping element is the actual thing that might tip. So a component of the climate system, and they have this part of the definition is that it has to be big. So subcontinental or larger. So subcontinental meaning like maybe the size of India or something, or larger, in which little causes can have big effects. So that's one of the same principles over here. And then the tipping element can have a tipping point. So the tipping element's tipping point is the critical threshold at which the small change in forcing. So usually we're thinking about the forcing, pushing something being temperature, that we're raising temperatures and then something is responding to that. So the tipping point would be the threshold at which the small change in, say, temperature triggers a disproportional response, like sea ice melt or like ice melt. So what's really important here is that under this definition, the crossing of a threshold commits us to a change, but the change itself could take centuries or longer to be realized. So this is one of the key differences between the kind of popular notion of tipping points, the straw that breaks the camel's back, or what they're talking about in this book, and climate tipping points, where it's really just kind of the intrinsic timescale of the Earth, that something that happens on 100 or 1,000 years is really abrupt in terms of geologic history, but that's a long time for us. So we don't really consider that instantaneous, right? But for something to be a tipping point in the climate system, it can be the case that you're committing the Earth to some change that may take 100 years, may take 1,000 years, may take multiple millennia. And so it's not part of the definition that it has to happen in a year or a month or something, very quickly like that. And then another part is this concept of irreversibility, at least on human timescales. So you can argue that a lot of things are reversible in the long run and tens of thousands of years or hundreds of thousands of years, but not reversible, at least on the timescale that we care about, so decades to centuries. So if we go back over to our three components of the Gladwellian tipping points. Contagiousness is not part of the definition of tipping points in the climate system. So all of Gladwell's tipping points are thinking about social contagion, right? The movement of ideas from person to person, and so that's not a part of what's going on over here. And then we're not gonna have this part of the definition of that the change happens not gradually, but at one dramatic moment. That's not part of it. So the only thing that really is the same between the two is that little causes, that you're at some parts of the system where a little cause can have a big effect, a big outcome. So those are already our first two learning outcomes here. So this kind of definition of tipping element and tipping point. And I'll give examples so this will become clearer. And then the difference between this popular notion of the tipping point and tipping points in the climate system. So here's our definitions. And then the big difference is really that tipping points in the climate system commit us to a change, but that change does not necessarily happen quickly the way we would typically think of the word quickly. Okay, so just some important caveats here before we get into some more details on tipping elements and tipping points. This main paper that's cited the most about tipping elements in the Earth system or in the climate system, this was not a paper that like established a bunch of very scientifically rigorously defined tipping points. Instead, really what this paper was kind of like a summary of a brainstorming exercise of what tipping points might be in the climate system. And so this is kind of expressed here in this paragraph from the paper. Many of the systems we consider do not yet have convincingly established tipping points. Nevertheless, increasing political demands to define and justify binding temperature targets, as well as a wider social interest in nonlinear climate changes, make it timely to review potential tipping elements in the climate system under anthropogenic forcing. So the point of this paper was just to say, okay, we've gathered a bunch of experts together, and we're going to write a paper on the parts of the climate system that we think might have some tippy elements to them. And another caveat is that there is definitely not one single established level of global warming that is like widely accepted to be a tipping point in the climate system. So this is a paper that kind of expresses that, called Catalog of Abrupt Shifts in Climate Models, essentially. And so they're saying that there are abrupt shifts, there are kind of tipping, kind of thresholdy things that we see in climate models, but there's no compelling evidence for a general relation between the overall number of abrupt shifts and the level of global warming. So there's not just some level of global warming that, like, for example, you're looking at in your En-ROADS calculator, at which that sets off all of these tipping points or tipping elements at once. There's different levels for different things. So tipping points are relatively speculative, and there's not necessarily a relationship between global average temperature and a bunch of tipping elements being tipped at once. So the Paris goals, so this is a screenshot of meeting the Paris goal of +2 degrees Celsius. That is a goal, 2 degrees Celsius above pre-industrial levels, but that's not because there's some well-defined tipping point at 2 degrees Celsius. So 2 degrees Celsius kind of, that was established in 2009. It kind of just was a nice round number where people were like, this might be a good goal to have that kind of balances concerns about how long it would take to decarbonize the economy versus impacts of climate change. So keep that in mind, that kind of came out of political and diplomatic discussions, and it didn't come from like some scientific report that said, okay, 2 degrees is exactly where humanity needs to aim in terms of global warming. And then the 1.5 was just like added on kind of after. So first 2 degrees was established as a goal, and then in subsequent negotiations, 1.5 was added as like, it's kind of like saying, it's like people get together and they're like, I say we should donate $100 to charity, and then someone else says, I say we should donate $200 to charity, and everyone's like, oh yeah, pat on the back to that person. That's kind of what happened, is that like, we had a goal of 2 degrees Celsius, and then a bunch of people were like, well, how about let's make the goal 1.5 degrees Celsius? And everyone's like, yeah, okay, let's make the goal 1. But meanwhile, we're not even close to to meeting the 2 degrees Celsius thing. So might as well, my goal is 1 degree Celsius. Oh, give me some credit for that. Like it was more like a social thing. And so we are going to cross 1.5 degrees Celsius almost certainly, and we will likely cross 2 degrees Celsius. Something interesting about these goals, though, is that they're really for 2100. So you could technically meet the goal even though you cross 1.5 degrees Celsius or 2 degrees Celsius, if you're able to come down, back down to 2 degrees Celsius in 2100. And so you would need to get CO2 out of the atmosphere in order to do that. So this point here that the Paris goals of 1.5 and 2 are not tipping points, I think is important because that was widely misreported when the last IPCC report came out, not the one that came out this fall, but a previous one that came out in 2018. There was a report that was on the impacts of global warming at 1.5 degrees Celsius above pre-industrial levels. And so the report is just saying, these are the impacts of global warming when it's 1.5 degrees Celsius. And then it was compared to the impacts at 2 degrees Celsius. And kind of the idea is like, how worth it is it to limit global warming to 1.5 degrees Celsius versus 2 degrees Celsius? But it really had nothing to do with tipping points or thresholds, or like, if you cross 1.5, then all this other stuff happens that you don't get below 1.5. Like most of these impacts are on sliding scales where, each degree warming makes the thing worse. So this is just an example headline from New York Times from their podcast that really falsely reports on what this IPCC report says. So it says a new climate tipping point. And then if you listen to that podcast, they talk about this report as if, scientists went back in the lab and they said, oh, we discovered a new tipping point in the climate system. It's 1.5 degrees. And now we're going to write a report about that. And that's really not what happened. It's like, it was the other way around. It was like politicians said, what are the impacts, scientists, at 1.5 degrees Celsius? Tell us what those are. And that's what this report is. So it's not a tipping point. The reason this kind of bugs me is that I'm quite sure that we are going to pass 1.5 degrees Celsius, and then it will, there'll be all these like reports about like, I thought scientists said that there was a catastrophic global tipping point at 1.5 degrees Celsius, and we don't see that. And so this, undermines the credibility of climate science. And it's frustrating because it's just not the case that this report said that. Okay, so this caveat over here that there's not necessarily a tipping point in terms of global temperature that cascades through everything. That's important to note. But we do know for sure that some elements of the climate system are tippy or display tippy behavior. And we know that just because we can see that in various geological evidence. So this is an example of a part of the climate system that we know to be very tippy, very nonlinear, very sensitive. And this is the temperature at the top of the Greenland ice sheet. So this over here is a proxy for temperature, this delta 018. But all that matters here is that as you go up, it's warmer at the top of the Greenland ice sheet. And as you go down, it's colder at the top of the Greenland ice sheet. And you're looking at time on the x-axis here. And so this is 80,000 years ago, 60,000 years ago, 40,000 years ago, 20,000 years ago, and then present day. And this comes from an ice core. And so recently, we've been in this relatively stable climate called the Holocene. But when we go back in time and look at the temperature at the top of Greenland, we see all of these what are called Heinrich events or Dansgaard-Oeschger events, which are these just very large changes in temperature at the top of the Greenland ice sheet. And we know that these changes were not caused by some like well-defined external forcing or external cause. So it's not like the sun got a lot brighter or there was a large change in well-mixed greenhouse gases. These are somehow coming about through like nonlinear interactions within the climate system. So some small change is causing something to be very tippy and to move in one direction or another very quickly. In this case, have large consequences in terms of temperature at the top of Greenland. So that just is to establish that we know for a fact that there are parts of the Earth system that do act very nonlinearly and do have very large responses to relatively small pushes. Okay, I'm going to pick up on this irreversible concept here as one of our important characteristics of climate tipping points. So this is a kind of an illustration of this irreversible concept, at least on human timescales. And so I'm going to compare the left side is a threshold response, but it's reversible, and the right side is a threshold response, but less reversible, where threshold refers to this idea that you can get a big change, in this case with a small amount of global warming. So I'll just put what these graphs on here look like first and then go through that. So it's like, let's say you start over here, you're at like 1 degree Celsius plus, plus 1 degree of global warming from pre-industrial. And then over here on the y-axis, it doesn't really matter what it is, but it's just something, it's the eventual response of something that you care about. So let's say it's the amount of ice melt, sea ice melt in the Arctic or something. And so the idea here is that you're increasing global warming and you're getting, an increase in that thing, you're melting sea ice, and then you're increasing global warming a little bit more up to this like cliff, up to this kind of threshold portion of the system, where then all of a sudden it can kind of take over, and there's some type of self-reinforcing mechanism that causes this thing to respond very largely without changes in global temperature. And so then if you warm more, then let's say you have very little ice left, and so you're not melting as much ice. But this is something, the way that this is drawn, this is reversible. So if you start now reversing global warming, you start cooling the temperature, then you can fall down the cliff the other way. So positive feedbacks work in both directions, right? So the ice albedo feedback is the one we talk about the most, and it's probably the most intuitive. That we talk about, that if you melt ice, then you have more low albedo ground exposed, which causes more absorption of solar radiation, which then warms more and causes more ice melt. But it goes in the other direction too. Positive just means self-reinforcing. It doesn't mean warming or something. So if it gets colder, then you have more ice covering more ground, then you're reflecting more solar radiation back to space, so it causes more ice. So these threshold responses can be reversible if you go in the other direction. But what we're worried about a lot of times in the climate system is these less reversible responses. So if we go over here, this is the idea that like you're doing the same thing, you're warming, you reach some cliff, some point where there's some type of self-sustaining reinforcing aspect to what you're looking at. Then you can warm a little bit more. But now let's say you start turning down the temperature, you start cooling it. And what happens is you can cross the same threshold, but then you don't actually fall down that same cliff. You're not like stuck in this other state. So it'd be like if you melted your ice away, and now you're starting to cool, but you can't get that like inception of the ice back. And so you're kind of like stuck in an ice-free area. And so maybe you could cool it more and eventually get down to another cliff, another threshold. But it took you more cooling to get that thing to reverse. So that's why I'm saying less reversible up here is that you can't just reverse it by going back in the other direction, but you can reverse it if you like really push it far. So I'll just show that again with a more concrete example. So this is the same idea, just with thinking about global temperature here and energy coming in from the sun. So these are just arbitrary units. There's no watts per meter squared or temperature on here. But let's say we're starting off over here with 0.85 arbitrary units of energy coming in from the sun, and we start increasing the energy coming in from the sun. We're going to turn this up. Okay, so we're getting a little bit of warming. So now we're at 0.9 units here. So this is 0.9. That's why I'm saying that here. And then this is 0.88 of temperature. And we're going to keep turning up the sun. We're now up to 1 unit and 0.9 units of temperature. So we're warming the planet because we're turning up the sun, and we're going to warm it a little bit more. And eventually it gets warm enough so that the ice sheet starts melting. So the ice melt becomes substantial. And let's say that then initiates this self-reinforcing feedback. And so then you can like start falling off this cliff where the ice melts by itself without you not turning up the sun anymore. The sun is just staying the same way. But now your temperature spiked up, your global temperature spiked up because you initiated some self-reinforcing feedback with the ice albedo feedback. So now if I start turning down the sun, what happens? It's too hot for the ice to be there. So I'm stuck up here where the global temperature is now 1.075, even though my energy coming in from the sun is 1 unit. And before, when it was 1 unit, I had a global temperature down here, right? So when I had the ice sheet there and the sun was at 1 unit, my global temperature was 0.9, but I warmed too much. I melted that ice sheet away. And now, even if I turn down the sun to 1 unit, my global temperature is 1.075. It's up here. So I did something that's difficult to reverse. Okay, so this is a vocabulary word, this thing that I'm describing here. This is called hysteresis. So this means that global temperature depends not only on the energy coming in from the sun, it also depends on whether the ice sheet is present, which depends on what happened in the past. But yeah, so hysteresis just means that that what you see depends on the history of the system. And so this is like, this is kind of an interesting way of thinking of it. If you remember from math in high school, algebra or pre-calculus, you'll come across like the definition of a function, where it'll be like y equals f of x, right, is the definition of a function. And that could be like y equals f of x equals x squared or something. And part of the definition of a function in math is that if I give you x, if I give you something here, you can tell me what y is. So there's something called like the vertical line test, where functions, if you put a vertical line on your graph, they never cross the line multiple times. There's only one value of y that corresponds to every value of x. And the real climate is not like this. So the real systems do not tend to be like this. They tend to be like this other case with hysteresis, where if I give you x, in this very kind of idealized case, you can tell me, well, there's 2 possible cases of global temperature. So if I give you how much energy is coming in from the sun, you can give me, well, there's 2 possible global temperatures, and it depends on the history. It depends on if there's an ice sheet there or not. So obviously, like, there's things that are much more irreversible than ice sheet growth. So like the Great Barrier Reef dying, so that would be something that's like totally irreversible, right? That like if you cross that threshold, like let's say this is the amount of extinction in the Great Barrier Reef, and so you're warming, and then you get a bunch of extinction at the Great Barrier Reef, and then let's say you start cooling. The Great Barrier Reef is not going to spontaneously reproduce, right? Because you went back down to the temperature at which it started causing extinction. So once you cross that threshold in one direction, that's irreversible going in the other direction. And so that would be a much more irreversible case. Okay, so hysteresis is the dependence of the state of the system on its history. And really, like, lots of things display this. Like, this is something that we kind of formalize in physical science, but it's actually very intuitive. So like, for example, the popularity of a lot of things displays hysteresis, the dependence on history. So for example, sports, like the popularity of sports, so American football in the United States or cricket in India, like these are examples of things that it's basically this self-perpetuating cycle that like depends on history. It depends on all these contingencies through history. And so then you get to a point where, it's like the self-sustaining thing where the sport is in the media a lot. And that means like a lot of people want to play the sport. So there's many opportunities to play the sport. And then there's public interest in the sport, which causes it to be in the media a lot. So it's just this, self-reinforcing established thing. And we know that the reason that like American football is popular in the United States is because of a bunch of historical accidents. So like if we happen to erase like everyone's minds in terms of football, for example, if we erase everyone's memory of American football overnight and waited 50 years, would the popularity of American football reemerge? Like almost certainly not, right? Like that's just something that happened through a bunch of historical accidents. And just the fact that different countries have different most popular sports like is very good evidence that it's not really the intrinsic nature of American football that makes it so popular in the United States. It's just historical accidents that lead to these kind of self-sustaining situations. And of course, we see this with all sorts of things that are popular, like celebrities, or celebrities are a good example, that they're in the media a lot, and then people are interested in them because they're in the media a lot, and there's kind of like this self-sustaining thing where like if you were to erase everyone's memory of a celebrity, like if you were to erase everyone's knowledge of Kim Kardashian, for example, it's not like it's not like she would spontaneously become popular again. Like her popularity depended on a bunch of historical contingencies, and then she's in this like self-perpetuating state where people are interested in her because people are interested in her. And so this is, you know, a digression, but this is important for all of our tipping points that we will be talking about. So this is a graphic from a nice article from Carbon Brief that discusses 9 tipping points in the climate system. And these are based on that Lenten paper. And so these are, I'll go over 5 of these, but just to list what they are. So Greenland ice sheet disintegration is a potential tipping point. Permafrost loss in the Arctic. Atlantic meridional overturning circulation breakdown. So that's potentially a abrupt shift in ocean circulation. Boreal forest shift, so shift in the range of forests in the northern high latitudes. Amazon rainforest dieback, so relatively quick die off of the rainforest in the Amazon. West Antarctic ice sheet disintegration, West African monsoon shift and Indian monsoon shift, and then coral reef die off. So I'm going to talk about these 5 tipping elements one by one. So Greenland ice sheet disintegration first. So we kind of already talked about this ice sheet stuff. Again, the most important notion here is that potential tipping elements in the climate system will have this self-perpetuating aspect to them. One kind of piece of evidence of that for the Greenland ice sheet is that if you just look at a picture of Greenland from space here, you notice that it's kind of lonely. Like, we know that it gets colder as it gets further to the north, right? But why is this piece of land covered in ice? And none of, like, Alaska is not covered in ice at the same latitude. Siberia is not covered in ice at the same latitude. Northern Europe isn't covered in ice at the same latitude. So it's not just like the latitude. It's not just how far north it is that causes Greenland to be covered in ice. And what it is that there's a self-perpetuating nature to it. It's kind of only there because it's there. It's there because of history, because of the fact that that ice built up there a long time ago, and that's the only reason it's there today. Essentially, the cycle of self-perpetuation for Greenland is that the top of the ice sheet is so tall that most of the precipitation that falls on it falls as snow. And so what that does is it causes enough ice mass to accumulate at the top of Greenland so that it's always balancing the ice that's melting on the outskirts, which, you know the ice has to be melting at the outskirts because the ocean is not frozen there. So we know that it's above freezing there. So this is this idea that, like, kind of no matter where you are, we know that, okay, we know the atmosphere gets colder the higher up it is. And so a lot of precipitation, a lot of rain starts as snow in the upper atmosphere, and then as it falls, it melts. So if you have an ice sheet that's up high, then a lot of that precipitation is going to fall as snow and land as snow on that ice sheet. But if it starts melting and goes down further, then you're going to have more of that ice sheet, more of that precipitation will fall as rain on the ice sheet as opposed to snow. So this ice sheet, the Greenland ice sheet, needs to be as tall as it is in order for it to sustain itself, in order for it to be there. And so when you start melting, or when you start warming and you start exposing more of the ice sheet to precipitation that's not snow and is rain instead, then you're going to start reducing its size. And when you start reducing its size, then less of it is exposed to snow as opposed to rain. And so you can kind of initiate this self-perpetuating feedback. So once you pull that out, then you can get it moving in that direction. And that is, what we see, right? So we've talked about in the observations of warming lecture that we're seeing a large reduction in ice mass from Greenland. This is like down like 4,000 gigatons of ice, where this is a gigaton compared to the Empire State Building. So losing a lot of ice. And again, a big part of that is that you are exposing more of the ice sheet to precipitation as rain rather than snow. So like, it's not really the ice albedo feedback, because it's not that we're just melting it from the outside and exposing more surface to solar radiation that's being absorbed. It's really this movement of the top of the ice sheet down, or getting exposed more to rain than snow. So I'm saying that the Greenland ice sheet may already be in this state of kind of this self-perpetuating feedback, where we are taking out this element and it's going to kind of move on its own. But then that brings us back to this important point. That's the kind of the difference between the Malcolm Gladwell tipping points and the climate system tipping points, is that you can cross a threshold and it potentially commits you to a change, but the change is not quick, at least how humans normally think of quick. So it commits us to a change, but the change itself may take centuries or longer to be realized. So our best modeling of the Greenland ice sheet melt looks something like this. So this is how much of the Greenland ice sheet melts in terms of how much sea level rise it would contribute. So sea level rise from Greenland in terms of meters, 0 to 8 meters, where, to remind you, a meter is 3.28 feet. And so we have 3 different emission scenarios, how much humans emit in terms of greenhouse gases, where 2.6 is kind of like meeting the Paris Agreement, and 8.5 is hopefully an unrealistically pessimistic emission scenario, where we kind of like find all of the fossil fuels we possibly can and burn them. And you'll see here that the point I'm making is that it takes a long time to melt the Greenland ice sheet. And you can see that by the year here, right? So the year is 2100 here, 2200, 2400, 2600, 2800, the year 3000. So we normally, see graphs out to the year 2100, and that's what your, En-ROADS calculator shows. But like for the melting of the Greenland ice sheet, like almost all of that melting on the high emission scenarios, or even these middle emission scenarios, happens in the next many centuries after the year 2100. So this is just what the ice sheet would look like in these various scenarios in the year 3000. So this is something that seems slow on our timescales. Something that's interesting is that it took millions of years to build up the ice sheet. So melting it in 1,000 years is actually very abrupt from a geological perspective. But it's just, it's not like this popular notion of like it happens in a year or something. Yeah, so this graph is looking at global temperatures through 65 million years ago to out to the year 2300. And so there's these different time scales here. So this is one time scale, and then it gets really expanded here and then really expanded here. So we're like sitting here in the year 2020. And the point of bringing this graph up here is that if you look up here, northern hemisphere ice sheets, this is showing that about 4 million years ago, that's when we first developed northern hemisphere ice sheets. So the like this Greenland ice sheet. And if you look at like what the temperature was to start those to develop, we're like right here on this graph, it's like 2 Celsius. And so we're talking about crossing that in the other direction, going forward, and crossing it by a lot under these like RCP 8.5 scenarios. So what that's saying is that we're warming the temperature warmer than what it was before, the Greenland ice sheet was initiated, before inception of the Greenland ice sheet. So there was no Greenland ice sheet, there was no northern hemisphere ice when the temperature was 4 degrees Celsius above this 1961 to 1990 average. And so we're talking about warming the climate that much. And so we don't expect that ice sheet to exist under that level of warming. And it took millions of years to build up ice in the northern hemisphere, including the Greenland ice sheet. And so melting it in 1,000 years is quick, actually. So I will put these potential tipping points on this graph of temperature. So this is again, the same emission scenarios, and then just looking at the year 2300. And just to get your bearings here, this is pre-industrial levels. Here's global warming in 2020. Here's our 1.5 and 2 degrees Paris goals. So these are adjusted because this isn't relative to pre-industrial. This is where we think we're going with current policies. So like if you actually look at what's proposed, rather than, countries sign the Paris Agreement, but then they don't actually have policies that add up to meeting the Paris Agreement. So if you add up what the policies say, then we are expecting global warming up here. And so then putting on there the Greenland ice sheet disintegration, there's like a time scale in the x-axis, and then kind of an uncertainty in global temperature on the y-axis. So we think that committing the Greenland ice sheet to eventual disintegration would occur between 1 degree Celsius and 3 degrees Celsius above pre-industrial levels. But then the time scale is centuries to millennia to have that ice sheet melt. And that's actually where, if you've heard of the organization 350.org, that number 350 comes from this same idea that we think that northern hemisphere ice started when CO2 levels went below 350. And so as long as we're above 350 on the other side, eventually we may be committed to melting all of our northern hemisphere ice, so Greenland. Okay, moving down to another ice sheet. This is something, we watched a little video, a Vox video on this, the West Antarctic ice sheet and the Thwaites Glacier. And so this is a similar one. It's a slightly different mechanism. So we have all this ice in the southern hemisphere as well. And you kind of have to think about how these ice sheets build up in order to understand the precariousness of this ice sheet. So you get an ice sheet in the first place because snow survives the summer. So you need it to snow on the ground, and it doesn't matter how cold it is in the winter. If it's warm enough in the summer to melt that snow, then you're not going to get an ice sheet. But if it's cold enough in the summer where the snow survives the summer, then the next year's snow falls on top of the previous year's snow. And with millions of years, then you can build up an ice sheet. And these ice sheets, can get so big that they totally depress the Earth's crust. And they weigh so much that they're pushing down the Earth's crust. And in the case of Antarctica, there is so much of this going on that now like a huge portion of the continent is underwater. So this is a map of Antarctica. If you were to remove all of the ice, this is what it looks like. With the ice, that's what we typically see. But you can see here that a lot of that continent is pushed down by the ice sheet underneath sea level. So right now it's kind of in this self-perpetuating state, the same thing as Greenland, where the top of it is tall enough so most of the precipitation falls as snow, and then there's enough ice mass that accumulates in the center to balance what's going on the edges. But if you start removing, you start melting it from the top, and so less snow is falling less precipitation is falling as snow, and more of it is falling as rain, then you're going to be taking out some of one of the self-sustaining elements. But there's another thing that's going on in particular with these ice sheets that are in a situation where they're like essentially sitting on a continent that's been pushed under sea level. And that's this thing called marine ice sheet instability. And that's basically that if you look at how the ice sheet depressed the continent, you can see like just intuitively that it's going to kind of push down more in the center than on the outside. And so what ends up happening is you get this thing called a retrograde slope, which all that means is that it's like sloping down as you go in towards the continent. And so when you start melting this ice sheet, what happens is like, this water is above freezing. And so the ice wants to melt when it's touching that water. And look at what happens when you start melting it. You are exposing more and more of the ice sheet to 32 degree and above water. You're exposing more and more of it to above freezing water as you're melting it because of this retrograde slope. Because the more you melt, the more of this thing is exposed, or this surface area is exposed to above freezing melt water. And so that is another one of these like potentially self-sustaining feedbacks. It's very uncertain. There's a lot of science going on with this right now, trying to figure out like how quickly this type of disintegration might happen. And if this is something that happens very quickly, that would be one of the mechanisms by which you could have like very large sea level rise on the order of decades this century, as opposed to that kind of like century to millennium timescale. If this happens very quickly. And so yeah, you can melt that ice sheet quickly because of that positive feedback, because of that self-reinforcing mechanism. And the concern, of course, is justified here with observations that we see with our gravity satellites, that we do have a lot of mass loss right in this West Antarctic region. So in this case, down like 2,000 gigatons of ice in Antarctica overall, but it's quite large in that given location. So putting West Antarctic ice sheet collapse on here, it's more uncertain in terms of temperature. where that threshold might be. So the range is 1 Celsius to 4 Celsius. And then this time scale is a little bit shorter, so I just have centuries on here rather than centuries to millennia. And it could, it's quite uncertain like how fast this positive reinforcing mechanism could work. And so there is a possibility that it's even like, significant sea level rise on the decade time scale. And that's one of the probably most prominent tipping points in the climate system, or tipping elements in the climate system that scientists are concerned about. And so I want to tie this together to your En-ROADS assignment by kind of showing you this in En-ROADS, or the best example of this that I can think of in En-ROADS. So here's our baseline in En-ROADS of 3.6 Celsius warming by 2100. And so let's do roughly a Paris Agreement mitigation strategy. So that would be +2 Celsius in 2100. So let's highly tax coal, oil, natural gas, put a carbon price on it to squeeze it out even more. Energy efficiency, electrification of buildings and transportation, and move this methane down. Okay, so here's a Paris achieving goal. So I want to show you the steps of the inertia here. So first of all, there's this is imagining that you highly tax things, you put a carbon price on, today, but you can still see that it takes a long time for this energy infrastructure to draw down. So, you're starting this in 2020, but you're not really, getting these fossil fuels down to close to zero until 2050s, 2060s. So there's this inertia just in the physical capital, call it, or just the physical infrastructure of the energy system, that we're not going to immediately be taking all of these power plants offline. It takes a long time for them to just kind of overturn and to naturally be replaced by, in this case, renewables. And so let's think about, okay, what is that going to do to CO2 emissions? Try to first picture that. Like, what is that going to look like for CO2 emissions? Remember the difference between emissions and concentrations. So here's our emissions. So this is, energy per year. And so in this case, even though like population is increasing and economic activity is increasing, we're getting a decrease in total energy use because we're increasing efficiency. So if we were to not have this increase in efficiency, then we would have this increase in energy use overall. But we're basically holding energy use kind of constant at, let's say 2000 levels. And we can see that better if we go to our Kaya graphs. The population is still increasing, GDP per capita is still increasing, but we're getting more efficiency in our economy. It takes less energy per unit of GDP or exchange to get what we want, and then less CO2 per unit of energy. So that's where we're getting the mitigation effects there. So our CO2 emissions are down close to zero. So going back to the bathtub analogy, our emissions are what's coming out of the faucet. So what do you think concentrations look like, CO2 concentrations? If this is emissions were going up, now emissions are going down, but note this number over here is important, right? They're still positive, but getting close to zero. So what are concentrations going to do? Concentrations would continue to increase just at a slower rate. So we have that. So there's a CO2 emissions tab in here, and then under impacts, there's CO2 concentration. So we can look at that. And so, yeah, so we're basically stabilizing CO2 concentrations in order to meet this Paris goal. So they're stabilized at about 440 parts per million here. And so this is where the bathtub analogy is not completely correct. It's, there's kind of, the drain is open a little bit. So that's why this emissions doesn't go absolutely to zero, and there's still some emissions. And so that's basically like there's some coming out of the faucet, and then there's some coming out of the drain. And so then the level in the tub stays the same over time. So what does temperature change with? Does it change with emissions, or does it change with concentrations? Like, was temperature going to look more like emissions or concentrations? Or another way to say this, if we look at temperature, will temperature be decreasing by the end of the century, or will it be steady or still increasing? Pretty much scales with concentrations. Is going to look pretty much like concentrations, but has a little bit more inertia where it's harder to stabilize than concentrations, because you've still got things going like ice albedo feedback going underneath, under the same CO2 concentrations. And so this is what temperature looks like. So you're meeting the Paris goal. You're getting 2 degrees Celsius in 2100, but it's still increasing by a little bit. And so now I want to show you, so it's kind of like, I'm showing you like these steps of inertia, that it's like, this is this immediate political action, which is unrealistic in itself. Like you can take it a step back at the inertia of politics and social movements and all that. Like we've known about global warming, well, since the 1800s. And we had like the first real papers on CO2 causing global warming in the 1930s. And there's been the IPCC since the late 1980s, early 1990s. And so all of that, takes a bunch of time for that to filter into the culture and filter into politics. And then policies have to be implemented, and then that filters through into like actual, changes in energy infrastructure. And then the changes in energy infrastructure take decades. And then the changes, then it's hard to bend down that curve of emissions. And then that only stabilizes concentrations, which only stabilizes temperature. And then we were talking about these ice sheets that, like, once we warm the climate, we've kind of started the ice sheets melting. And those have this self-perpetuating nature to them as well. And so it's really difficult to stop that once it's started. So we can also then look at these slower moving things like ice sheets. This is also an impact. And it would be manifested in sea level rise. Most of the sea level rise to date has been because of warming of the ocean and expansion of water. But in the future, it's more coming from this Greenland and Antarctic ice sheet melt. So picture in your mind what you think sea level rise is going to look like. Is it going to look like temperature? Is it going to peak and come back down? What's it going to do? Look at that. That's not good. This is a very ambitious mitigation goal. This is meeting the climate Paris Agreement, which is very unlikely to happen in the real world, in my opinion. And we're kind of just barely making a dent in sea level rise by 2100. And sea levels are just continuing to rise and will continue to rise for hundreds to thousands of years, even under this scenario. And the difference between baseline and all of this effort is pretty small for sea level rise. Another thing we can look at in this tool that I mentioned last time is this flood risk map developed by Climate Central. So this is just kind of looking at, just taking a global elevation map and increasing sea level and looking at, how much land would be at risk. And I just zoomed in here to, let's see if I remember. Yeah, so I'm in Santa Cruz. And so this is, in the 21st century, they have these two colors, land at risk and land saved by actions. And when you look at a lot of locations, there's not that much of a difference when it comes to sea level rise. So there's not like a bunch. So if there was a huge difference between the baseline and what you've done here in your mitigation strategy, you would see tons of green, tons of land saved by your actions. But that tends not to be what we see. So here's redwood shores. So that's, we can save that in the 21st century by our actions. When we take into account the much longer time frame, if we go long-term equilibrium, so that's like looking at the century to 1,000-year time scale, then we start getting more green, where we're saving parts of the shore from our actions, because it's it's simulating that the ice sheet does not melt as much in its equilibrium. Let's look back at Santa Cruz. So decreasing land at risk by maybe 30–40%, something like that. But that's just that's the nature of this system, of these long time lags and this long inertia, large inertia in the system. And so this doesn't mean that like it's not worth it to do it. This is just the sea level rise aspect of it, the ice sheet aspect of it. And of course, all of the other impacts that don't have to do with sea level rise, there's a huge difference between 4 degrees Celsius and 2 degrees Celsius. But it's just not necessarily the case with these ice sheets. They kind of like, once you get them going, they're moving slowly, but they're moving, and it's difficult to affect how much they're going to change. And for sure, how much they're going to change in the near term is in this century. So I was going through some other tipping points or tipping elements in the climate system, and I ended at this one, the Amazon rainforest dieback. And so the one sentence summary here is: deforestation and hotter, drier conditions causing dieback of the rainforest and a shift towards savanna. So it's kind of like going from, the idea would be that under global warming, you could go from like a rainforest type ecosystem towards a savanna type ecosystem. So much less trees, more grass dominated, and so, you know, much less biodiversity. So that would entail huge species extinction. So how does this one work? So first of all, here's where the Amazon rainforest is. Northern part of Brazil, Bolivia, Peru, Colombia, Venezuela. The important part of the rainforest is that rainforests need rain. And the way that the self-sustaining aspect of the rainforest works in this case, and what makes it a tipping element, is that rainforests also produce rain, interestingly. So what happens is, well, first of all, rainforests need rain, right? So why is that? Well, that just goes to our photosynthesis equation, that all plants need water as part of this equation. So they get carbon dioxide from the atmosphere, they get sunlight coming in from above, and they need water some from the environment, and that is going to come in as rain, and they produce their glucose and release oxygen to the atmosphere. So the water for the Amazon rainforest is coming from the Atlantic Ocean. So you have evaporation of water off the Atlantic Ocean, and it's advected in towards the continent, where you have condensation of the water into liquid water, and then it falls out as precipitation. And so that is providing our water to our plants here. Now, the plants, you know, some of that water falls on the surface and evaporates back to the atmosphere. And so that would happen without plants. But plants also transpire water. And so when you combine evaporation and transpiration, it gets called evapotranspiration. But transpiration is just, you know, the water is going up the plant's stem through osmosis, and some of that is released by the plant to the atmosphere, some of that water. And so it's not really using all of this water for photosynthesis, and it releases some to the atmosphere. And so you can kind of see how that would help, especially plants more inland, that you kind of have precipitation over here, and then the plants are putting some of that water back into the atmosphere. And a lot of the water that then is precipitated again is recycled in that way. So it's about half, 50% of rainfall in the Amazon is recycled or regenerated through this evapotranspiration. And so here's our kind of self-perpetuating system, that the rainforest produces a great amount of evapotranspiration, and the atmosphere produces a great amount of rain for the plants. And so the rainforest has this self-perpetuating cycle to it. So it's another one of these things that's kind of there because it's there, especially these plants inland, because the precipitation falls here, it gets evapotranspirated back up to the atmosphere, falls again, evapotranspirated back up to the atmosphere, falls again, evapotranspirated back up to the atmosphere. And so the plants inland are really relying on the plants or the trees further closer to the source of water, closer to the ocean, to kind of push that water inland through the transpiration mechanism. And this is just kind of a picture illustrating that's showing all these clouds over the rainforest that are really made possible by evapotranspiration. You would not see these clouds here if you took out the rainforest from underneath them. The rainforest is kind of producing those clouds on top of the rainforest. And so the rainforest produces its own rain, helping it maintain itself. Okay, so there's kind of three ways that we can intervene in this and cause kind of the tipping of the dominoes, and to pull out one of the elements of our self-perpetuating system. So one is kind of to reduce just the input of water vapor or water into the rainforest. And so that comes about because there is the potential that just the way that precipitation patterns will change under global warming, that we'll see a reduction in rainfall over the Amazon rainforest. And this is shown here. These are climate model projections under this pessimistic 8.5 emission scenario. So that's the large emissions through the end of the century. And this is showing purple are increases in precipitation, and brown are decreases in precipitation relative to today. And this is in percent of local precipitation. And so we see the stippling is kind of like where a lot of the models agree on the sign of the change. And so we don't have stippling here, meaning that there's not a lot of agreement. And so there's a lot of uncertainty with this projection. But you do see that it's brown there. And so the kind of best guess is that precipitation patterns will change so that there's less precipitation over the Amazon. And because of this positive reinforcing, feedback, the self-sustaining nature to the rainforest, reducing that precipitation can then perpetuate into the evapotranspiration and cause there to be less rain, a lot less rain inland, which can kind of initiate this positive feedback of collapse. So in that case, you'd be taking out this component that the atmosphere produces a great amount of rain at the beginning. And so if I were to alter this diagram, it would be kind of like, okay, less water is coming in here, so you have less precipitation, less evapotranspiration, and so then you're going to have less rainforest here, which could then continue to be self-perpetuating. So that's one, is just kind of decreasing precipitation because of how global warming affects global precipitation patterns. Two, this doesn't have to do with temperature at all. It just has to do with the fact that CO2 concentrations are increasing. And so this is that increased atmospheric CO2 makes plants more water efficient, and transpiration decreases. So the plants have to, open their stomata less widely to take in carbon dioxide when there's more carbon dioxide in the air, which means that they release less water to the atmosphere. They're more water efficient. And so that's good for that particular plant. But it's not good for plants that were relying on that plant's transpiration for their own water. So it could make it so that it's less easy to get this water inland for these plants that are inland when CO2 concentrations are higher. So that's another way, is kind of pulling out this component. Rainforests produce a great amount of evapotranspiration. Just increasing CO2 could reduce that. And the third way that this could be, the third most likely way that this could be perturbed this century, is just through direct deforestation. So not really a consequence of global warming, related to global warming, but just exacerbating these other two, is that if you literally just start deleting the rainforest, you're starting to take away trees, then you are taking away this transpiration from those trees. And so you are making it harder for the plants that are left to exist. So it's interesting, like if you were to take like this, so let's say this is rainforest here, and let's say you deforest all around it for hundreds and hundreds of miles. Like my first intuition would be like, well, this would be fine. You didn't do anything to this, and like the climate shouldn't change. You're at the same latitude and everything like that. But actually, it would. This patch relies on the whole rest of the rainforest for a lot of its water, and so it would get less water just because of the deforestation all around it, and make it, that's the whole point here, is that you're making it less likely to exist because it's all this self-reinforcing mechanisms going on. So this one is, when I'm putting these on this, this diagram showing temperature and time, showing where the possible tipping point might be. So our modeling on this indicates that it's between 3 and 5 degrees Celsius above pre-industrial levels. So meeting the Paris goals would keep us kind of well below that, but current policy trajectory puts us right up to the edge of that. And then the transition time is much faster than the ice sheet ones. So the ice sheet ones were hundreds of years to thousands of years, where this is something like 50 years that you kind of switch rainforest into savanna. So that's as fast as anything on this list. So it's kind of getting closer to that like true tipping point notion, where it's happens in a short amount of time. So I'm going to talk about two more. So one is this ocean circulation, the Atlantic meridional overturning circulation breakdown. So this is a important ocean circulation in our climate system. It's called Atlantic meridional overturning circulation. So what do those words mean? So Atlantic, it's in the Atlantic Ocean. Meridional, that means north-south. That's a word we use a lot in meteorology and geography. Where zonal means east-west, meridional means north-south. Overturning tells you like the orientation of the circulation, where overturning means like it's in the vertical. So if I'm doing a circulation like this, where you have an up component and a down component, and like a south and a north, that's an overturning circulation. So as opposed to actually what you're looking at here, which is a circulation in the plane parallel to the surface of the Earth. So overturning means you have like an up down part. and circulation means it's circulation. So this is important in the climate system because it transports a bunch of heat, a great amount of heat from the tropics into the northern high latitudes. And some of that heat influences Europe's climate and makes its winters milder than they would be otherwise. And this is what this figure is showing is like the top. Yeah, it's the top of the circulation in orange here. And so the Gulf Stream, this often gets like confused with the Gulf Stream. The Gulf Stream is kind of a part of the circulation. It's an important component, but that's really like just the Gulf Stream is a river of water just in this kind of section of the Atlantic. And so it's not the entire circulation that we're talking about here. But overall, what this is showing is that you have warm water moving to the north in the Atlantic, where it then sinks, and this blue river of water is at the bottom of the ocean. So this is at the surface, sinking up here, and that's why this is called deep water, North Atlantic deep water. Sinks down to the depths of the ocean and then moves back south. And this whole circulation can be thought of like a conveyor belt. And that makes sense because we have conservation of mass, where if I just like start making water sink in one location in a bathtub or something, that's going to be replaced by water coming in from the side. It's not just going to create a hole of water, right? So once you move water somewhere, it's going to move water everywhere. And in this case, it's kind of like a conveyor belt where it's down here and then goes to the south, and it's kind of complicated throughout the rest of the world, but then it's going north at the surface here. So this would be the top of the conveyor belt at the surface, and then the bottom of the conveyor belt going south. So the kind of, we think physically, like the critical part of this conveyor belt is that the water has to sink in the North Atlantic. And that happens, water sinks when it's heavier than its surrounding water, or when it's more dense than its surrounding water. And the way that happens is that you have this kind of warm water going to the north, and the atmosphere up there is much colder than the ocean. And so it takes out a bunch of heat from the ocean, and it also evaporates a bunch of fresh water out of the ocean. And so what's left is colder, denser. So salt water is denser than fresh water, and cold water is denser than warm water. And so the atmosphere kind of pulling those lighter elements out of the water makes that water denser than its environment, and it sinks. And that is like this critical link in this conveyor belt, where if you were to get rid of that, then you could shut down the whole conveyor belt. So here's our self-perpetuating system. Import of warm water, that's this part, able to give heat to the atmosphere. The atmosphere takes that heat, makes the water denser than its surrounding environment. So then you have sinking water. But then that sinking water is kind of what's drawing back up this water from the south. So we could mess with that in a few ways. One, this is very close to the Greenland ice sheet. We are melting the Greenland ice sheet. Greenland ice sheet is made of fresh water, not salty water, because the salt doesn't evaporate, and the Greenland ice sheet is made of rain that fell as snow that condensed into ice. So the Greenland ice sheet is fresh. And so if we were to melt a bunch of this, we're putting a bunch of fresh water into the North Atlantic, making it less dense, less easy for it to sink to the bottom of the ocean. And so you could kind of be putting, your finger on the conveyor belt here and trying and like stopping it. We also expect there to be increases in rain in this location. We go back to our projection. Overall in the North Atlantic, this is purple, showing that we think that there will be an increase in rain in that location. And the increase in rain is an increase in fresh water. And so that would also cause this water to be not as dense as it is currently, and make it harder for it to sink to the bottom of the ocean. And then the warming of the atmosphere itself, the atmosphere warms faster than the ocean. And so a warmer atmosphere is less able to pull heat out of the ocean. And again, that's going to make the ocean stay warmer. And so it's not going to be able to create this increase in density that causes it to sink. So these three things, I think, are going on under global warming, making it harder for the water to sink here, making this conveyor belt slowed down and potentially could collapse under enough warming. And collapse meaning like there's no more movement of this water. And so we actually see, I mean, these are like kind of our theoretical reasons to expect this, but we do see just direct evidence of this as well. So I've shown this graph, this map before of temperature trends over the period that we've had good records. So basically, since there's been a lot of emissions of greenhouse gases to the present, so 1880 to 2020, and we see warming almost everywhere, except in this North Atlantic region, where we see a little bit of cooling. And we do think the most likely explanation for that is that we are slowing down this ocean circulation. We're slowing down the transport of heat into the North Atlantic, and so then causing this local cooling effect there. And this was the premise of a movie in 2004 called The Day After Tomorrow, the only movie that I know of where a climate scientist is the protagonist hero. So I like that movie, except it's very, very inaccurate. And this is one of its inaccuracies, is that it basically shows New York and Europe freezing overnight, or like in a matter of hours or days, but it's based on this same mechanism. I mean, it's based kind of roughly on a real idea, but just kind of showing that it would happen on this crazy, unrealistic time scale. And we actually don't expect cooling to be large enough to overcome the warming from CO2. So our best guess would be that you would get less warming because of this mechanism, not actually cooling relative to today. This is a map of the effect of shutting down the Atlantic meridional overturning circulation just by itself. So you're showing cooling and warming only from the impact of shutting down this circulation. So not like under a situation of global warming causing it, because then you'd have additional warming on top of this. But so if you were to shut down the circulation, this is coming from physical climate models calculating what would happen. It would cause like the entire northern hemisphere to be colder than it would be with the circulation, and especially in the North Atlantic and in Europe. And so if we look at projections from climate models, this is from the last IPCC report. This is like all of the different physical climate models together. And this is showing surface air temperature change in the last couple decades of the century, so 2081 to 2100. And this is showing the amount of warming over that time period under like a middle emission scenario. And so we can see that there's disagreement from the climate models, where some models, if you take this, there's not like any signature really in the North Atlantic that shows that it's particularly different from anywhere else, maybe slightly less warming there. Where some models like this one, this FIO or system model, that one shows a huge amount of cooling actually locally in 2100 because of this mechanism, because of this shutdown in the circulation. So if you kind of like average them all together and kind of take that as your best guess, then we don't really expect this century to see cooling in that region. But some models do produce that. Some models do actually show that. So it's a possibility. And if it shows up in a physical climate model like this, it's physically possible, and it's within our like uncertainty of how the climate system works that it could happen. So this is showing for sure like Norway and Sweden seeing significant cooling by the end of the century because of this. But even some of the other ones that show local cooling, it doesn't really propagate into the continent. Like it's kind of localized in the ocean section and not actually where people live. So this one we think would be breached. It's kind of a similar temperature threshold to the Amazon dieback, so like 3 to 5 degrees Celsius, and then would take roughly 100 years to transition. Okay, so last one I want to talk about is this permafrost loss, abrupt increase in emissions of CO2 and methane through the thawing of frozen carbon-rich soils. So this one is probably like the most famous tipping point as far as I can see in the media. I'll remind you that we talked about this a little bit with carbon feedbacks, this idea that there's carbon in the land, especially in the high latitude, cold parts of the Earth system, that when you start warming the climate, it releases that carbon to the atmosphere, both CO2 and methane. And so this particular one is permafrost loss. So first of all, permafrost is frozen ground that contains frozen organic material. Permafrost The definition technically is ground that's frozen for at least 2 years. I wouldn't call that permanent, but that's the name that it's given. So it has to be frozen for at least 2 years straight. So essentially that's meaning that it's not, thawing every year. It's not thawing in the summer. It's frozen throughout the summer. And it contains organic material, but the microbes that would like to eat that organic material can't because it's frozen. So it's like taking your leftovers and putting them in the freezer. They can stay there for a really long time. They're not going to break down. They're not going to go bad because the microbes don't break them down. They can't eat them when they're frozen. But if you start to thaw them out, your food, if you take your frozen food out of the freezer, it will go bad. And the same thing can happen here. As you start thawing this organic material, then the microbes can start to eat them, and they can then release through their metabolism CH4 or CO2 to the atmosphere, causing increases in greenhouse gas concentrations in the atmosphere. And so it turns out that this is certainly irreversible on human timescales, that you can't get that carbon back into the soils, within the next decades to centuries. So it's kind of like the tube of toothpaste, where you can't get that toothpaste back into the tube once you squeeze it out. What's important is that it's absolutely true that this is a positive feedback on warming. But what I see anyway in the media a lot is the notion that this is a true tipping point that's going to cause like runaway global warming. That you warm the Arctic, it releases carbon to the atmosphere, and then that additional carbon to the atmosphere is going to cause more warming, and then that just is snowballs. And so then there's nothing we can do, and it's over because we're just going to warm to become Venus because of this situation. But that's not what we think. The summary here: large amounts of organic carbon are stored in permafrost, ground that remains frozen throughout the year. If significant areas of permafrost thaw as the climate warms, some of that carbon may be released into the atmosphere in the form of carbon dioxide or methane, resulting in additional warming. So it's a positive feedback. Projections from models of permafrost ecosystems suggest that future permafrost thaw will lead to some additional warming, enough to be important, but not enough to lead to a runaway warming situation, where permafrost thaw leads to a dramatic self-reinforcing acceleration of global warming. So it's a positive feedback, but not a self-sustaining positive feedback. And so not really a tipping point situation. It's really just a positive feedback in the sense that it causes more warming than we would get without that in the system. And this is just another passage from the recent IPCC report talking about something similar that I brought up last time about there not being like a global temperature that tips and causes runaway warming. It says there's no evidence of abrupt change in climate projections of global surface temperature for the next century. There's a near linear relationship between cumulative CO2 emissions and maximum global mean surface air temperature increase caused by CO2 over the course of the century. So they're just saying that the more CO2 we emit, the more global warming we'll get this century. The less CO2 we emit, the less global warming we'll get this century. And it's not a situation where we may have crossed some global tipping point with temperature where we've released enough CO2 where now we can no longer control global temperature. There's these kind of local tipping mechanisms where we may not be able to reverse the melting of the ice sheets, for example, but that does not apply to global temperature. Okay, so I've summarized these tipping elements in this table. So these are the 5 that we talked about. So the melting of the 2 main ice sheets, the Atlantic meridional overturning circulation shutoff, Arctic permafrost melt, Amazon rainforest dieback. I have the potential reason for it being a tipping point. So there's some type of a feedback or some type of a self-sustaining element to it. Here is where we think we may be committed to tipping. And so for the Arctic permafrost one, I don't have things in there because it's really not a tipping point or a tipping element. And then the timescales that those could be realized. So the fastest one we looked at is the Amazon rainforest dieback, could be something like 50 years. And then some key impacts of those. And then I put on here, just as kind of a hopeful one, is energy transition. So transitioning from fossil fuels to energy sources that don't emit CO2 and other greenhouse gases as a byproduct. This kind of would go back to the Gladwellian tipping point concept, where you have some type of social or political contagion that's informed by all this science, informed by what we're talking about today, that causes society to switch and there to be some type of a tip into transitioning our energy system away from fossil fuels. And one thing that might help with that is this drastic reduction in the cost of alternative sources of energy. So this is another thing I pulled from En-ROADS, looking at the cost of solar electricity from 1990 to 2020. And we see this just huge reduction in the cost of solar electricity. So that really helps the potential for tipping. So like by some measures in some locations, wind and solar is cheaper than fossil fuels, or at least new wind and solar is cheaper than fossil fuels. And so once that's the case, then that's kind of like intrinsically a tipping type of thing, right? That like once you kind of cross the threshold where one thing is cheaper than the other one, then want to buy that cheaper thing. And so that makes it more likely to kind of tip in that direction. But there's a lot of challenges with once you move to more and more wind and solar, you're using more and more land, and it becomes more and more difficult to deal with lulls or droughts in wind and solar resources, things like that. But I do think that the energy transition itself, kind of ironically, could be considered a tipping element, and we will see if that's the case.